Hey guys, we are starting chapter 12. It's our very last chapter for the year. And this chapter is called More About Regression, and 12.1 will be actually making inference about regression, and 12.2 will be linearizing data so that we can run the least squares regression. So let's just get started by reviewing what we did in chapter 3, which was the least squares regression analysis. So what we have here is actual population data from Old Faithful Geyser, and we're trying to determine if there's a relationship between the duration of the eruption and the interval between eruptions. So remember that when you have two quantitative variables, you want to analyze them with a scatter plot, and you can also see after the regression was run, they also did a residual plot here. But you want to make sure for the scatter plot that you use your acronym DOFS, direction, outliers, / anything unusual you see about your data, form, and string. So we're going to analyze this scatter plot. So direction. So you can see this direction is positive, and what appears to be happening as the duration of the eruption increases, so does the interval between eruptions. The next thing is outliers. There really don't appear to be any outliers unless these two up here might be a little unusual. There's a little, blip here or there, but overall most of the data falls in that overall linear pattern. And the other thing that you might want to comment on is there are two clusters in the data, but they still follow the same pattern. Form. The relationship is linear, and it appears to be fairly strong. So the real question is, how are we going to actually be able to run a regression on the entire population? Well, you really usually would not be able to do that. So as everything we've done this second semester, we're going to use inference. We're going to take one sample, and we're going to learn about the sampling distribution of our statistics for regression, and we're going to learn how to infer back to the population. So let's start by taking a look at how we would accomplish this. So say we take SRSs of size 20 from the eruptions, and we generate models. Excuse me. So these are three models that have been generated, least squares regression lines. And you remember that y hat is your predicted y. You have your a value, which is your y-intercept, and you have your b value, which is your slope. And we really focus more on slope in AP statistics. We interpret that. We really are going to do inference on slope for this unit, so just let you know that. So you notice that all three of these slopes are different. So how are we going to take one population and one sample slope, one sample from that population and one sample slope to infer back to the entire population? Well, we need to learn about the sampling distribution of slope. So first of all, let's review some terms here. So what is the difference between a sample regression line and a population regression line, which is actually the true regression line? It's sort of like when we want to know the actual mean of a population, we only take one sample mean and then we can infer back to the population. So for the sample regression line, the statistics are going to be A and B. I kind of mentioned that already. So we have A and B, and it's used to make predictions. We have y hat is equal to a plus bx. While the true regression line has the parameters, these are population parameters, alpha and beta. And you can see the y-intercept from the sample kind of corresponds to the y-intercept from the population, and the same thing for the slope. And the model we're going to be running here is mu sub y. So we want the average response, and we're going to predict it using alpha plus beta x. And like I said, we're going to focus only on the slope, and we're going to generate confidence intervals, and we're going to do significance tests about the slope. So let's learn how to do that. Okay, so what does the sampling distribution of B look like? So we took 3 samples a minute ago of size 20. Here we have, it's basically done with a computer program. We have 1,000 samples that have been generated, the sample regressions have been run, and then we have the slopes from each of those 1,000 samples. So remember, this is just an approximation of the sampling distribution. The actual sampling distribution would be every single sample of size 20 from the population, and we would get every single slope from that. So overall, you can see the shape is of B values. Remember, that's what we're looking at here, is roughly symmetric and unimodal. And if we were to do a normal probability plot, it would basically look normal. The shape of the true or the actual sampling distribution would be normal, so that's important for us to be able to use our slope to infer back to the population slope. The average or the mean of all 1,000 B values here is 10.32, where the actual beta is 10.36 from the population. So you guys should recognize this terminology here, or this notation here. We have the average or the mean of all the slopes will be equal to beta, which is 10.36, if we had every single slope. And that is because B is an unbiased estimator of beta, and that's really important for us to be able to infer back to the population. And down here, and I'm going to go into this more later, but the spread will be roughly 1.30. I think the actual slope, the actual standard deviation is 1.30. The standard deviation of our 1,000 B values was 1.31. And you can see here there's a formula that we're going to follow, and we'll talk about that in just a minute. Okay, now, we need to know our conditions for inference for slope or for regression. And this diagram right here illustrates kind of what you need to know for that. What we have is the actual regression line, the true regression line running through, okay? And then we have x's. Remember that we have explanatory variables and we have response variables along the y-axis. But what we have for every single possible x is its own little curve. You can see it there. So basically, we need to make sure that the average or the mean of all of the y's for this particular x is actually going to run along this line, or this line runs along those averages, I should say. That's one thing to take away. And basically, that's just saying that we need to make sure we have a linear relationship between x and y. The next thing is, you can see the bell-shaped curve here, the symmetry, unimodal. It is basically normal. So what this is saying is for every single x, we need to make sure our y's vary in a normal fashion. The other thing is, you can notice here sigma, this stands for standard deviation. Every single curve has the same standard deviation. So for that, we're going to make sure we have something called equal variance. So this diagram illustrates what we need to know for the actual conditions. I'm obviously going to give you a little way to memorize that, to know how to do that, but that's basically the understanding behind it, or the concepts behind it. So, as our book usually does, they gave us a little acronym here. So linear, but it's not quite linear. We have our A is missing, so you can call it liner, you can call it linear, however you want to remember it. But these are the acronyms that you're going to use to remember how to do the conditions. These are probably the hardest conditions we have had. They in fact are the hardest, but it's not going to be too bad. So linear, the true relationship between x and y must be linear. So I kind of talked about that already. How will we do that? Well, we will do that or verify that. Sorry, let me go back. We will verify that by doing a scatter plot and a residual plot. So that's what we're going to do for that, and I'll tell you in a minute how to analyze those. Independent, this is nothing new. We have to have individual observations that are independent of each other. Normal, now this is talking about for any fixed value of x, we need for the responses to vary normally. So we are going to do a normal probability plot on our residuals. So that's going to be pretty easy to do. Equal variance, and this is what I'm talking about here with the standard deviation. Every single x, you need to have your responses varying in roughly the same amount. So that's why we call it equal variance. And we are going to also do a residual plot for that and analyze that. Random, nothing new. The data come from a well-designed random sample or randomized experiment. So how do we check these conditions? Well, linear, we're going to examine the scatter plot to check that the overall pattern is roughly linear or of a linear form. You're going to look for curve patterns in the residual plot. So these are the two graphs we're going to do to ensure linear. You also have to do residual plot for a couple of the others too. So you're going to have to do it either way. So check to see that the residual center on the residual equals 0. It's kind of like y is equal to 0, the horizontal line. So those are the two graphs you're going to do, and those are the two things you're going to look for: linear form, and that you have a scatter about the residual equals 0 line. This is the same analysis we did when we actually learned how to perform linear regression analysis earlier in Chapter 3. Independent, look at how the data were produced. Random sampling and random experimentation will take care of that. And with experimentation, we need to make sure we do random assignment. If you are sampling without replacement, you need to make sure that your 10% condition is met. So you have kind of something to think about when you look at independence. Now, normality, and remember we need to make sure that for every x value, our y's vary normally. You can do a stem plot of your residuals, a histogram of your residuals, or a normal probability plot. I would probably just do the normal probability plot, but sometimes these other graphs can be given to you and you need to know how to interpret them. So you're going to check for any skewness that you see, because remember we're checking for normality here, and departures from normality. So that's how you're going to analyze the normal condition here. Equal variance, we're going to go back to the residual plot and make sure that the residuals are scattered above and below the residual equals 0 line. Okay, so that's how we're going to accomplish that. Random, you're just going to see if the data were produced by random sampling or random assignment or randomized experimentation. And guys, when I say randomized experiment, that kind of implies that you're randomly assigning to the treatment group. So that's what we're doing there. Okay, so let's do an example. Miss Barrett's class did a variation of the helicopter experiment. Students randomly assigned 14 helicopters to each of 5 drop heights. So that's kind of why the data looks kind of interesting here, but you still can analyze this for a linear form. Reading on, the helicopters were randomly assigned to the order, and the class used Minitab to carry out a least squares regression line, and these are the graphs that we're seeing here. So we have, basically this is a scatter plot, we have a residual plot, we have a histogram of the residuals, and we have a normal probability plot of the residuals. So pretty much it looks good to me. This is one thing to be a little concerned about because this is where we check for equal variance. All these others are pretty much varying above and below the line. This one is a little bit more spread out. So that's a little bit to be concerned about, but you probably just want to comment on that and make note of it and then proceed with the inference. Now, so this is summarizing what we just saw. The scatter plot shows a clear linear form. And for each drop height used in the experiment, the residuals are centered on the residual equals 0 line. The residual plot shows random, do this one first guys, random scatter about the horizontal line. So again, just making sure we have a good linear relationship and that the model is the right model to be using. Independent, because the helicopters were released in a random order, we have taken care of the independence condition. Normality, the histogram of the residuals is single peaked, it is unimodal, and somewhat bell-shaped. In addition, the normal probability plot is very close to linear, so we're good with the normal condition. Equal variance. So the residual plot shows a similar amount of scatter above the line y is equal to 0 or residual equals 0. However, flight times, flight times seem to vary more for the helicopters that were dropped from a height of 307. So that's what we were talking about there. So the helicopters were randomly assigned to the 5 possible drop heights. So we're pretty good. I would definitely want to comment on the equal variance, but we should be safe performing inference for regression, and basically we're going to focus on inference about the slope for this one. Okay, so this is your assignment. This is what you're supposed to do tonight and bring in tomorrow. We're going to check it in class. You're going to read this and you're going to do the full regression analysis, and you have more questions than this. But I just want to kind of remind you of what we're looking at here. When you're reading output from the computer, your constant, this is going to be your y-intercept, 85.706, negative 1.1171 is going to be your slope. So you're going to be using that to actually determine what the model is. They actually give you the model down there. Sorry about that. So the other things you want to comment on